Okay, now we're going to look at centers of the center of mass, and this is a nice application for engineering or physics that we can use with the things that we've been learning. So the main objective right here is to find a point on which a thin plate of any given shape balances horizontally. This point is called the center of mass. So just to, there's like a little picture on the handout I gave you of a surface balancing on a fulcrum, but if we just imagine like a seesaw, right? If you had like a seesaw right there, if somebody was heavier over here, it would go down heavier, and this person would be up, or vice versa. So, but if they weigh the same, right, it's going to be balanced. So, we want to know where the center of mass would be if people are not the same weight, or if masses are not the same amount. So let's just suppose, let's have let's don't center it. Here is our balance point, or our fulcrum, and let's imagine that we've got a mass on this end and a mass on this end, where this distance and this distance are different from each other. Okay, this is the distance, D1, and this is the mass, M1. And this is another distance, D2, and this is another mass, M2. Okay, so the question is, what point would these balance, okay? So it turns out that these will be balanced when the mass 1 and D1 is equivalent to M2 times this distance, D2. When this times this is equal to this times this, this is the point at which these two will be balanced. That's when that will be balanced. So we can, this idea of this is what makes something balanced is called the law of the lever, and it was discovered by Archimedes. And so we can expand this notion of this is how you can keep something balanced. In general, if we have a system of n particles with masses m1 through mn, located at the points x1, x2 through xn on the x-axis. Okay, we can imagine that. So let's just say, okay, here's an x-axis, sort of like a horizontal beam, and we've got these different points, x1, x2, x3, x4, x5 at these different x locations. Maybe this is where 0 is, and this is different masses, m2, m3, m4, m5. The question is, where would our center of mass be? Where would we need to put the fulcrum, so to speak, to keep our axis balanced? That's the question. So there is, based off of this principle, we can expand that into saying that the balance point, known as x bar, the center of mass, x bar, can be calculated to be the sum of the masses m sub I times their location x sub I divided by the sum of the masses m sub I. So these guys have names, and so these are going to be summed from I is 1 to n, and the number of masses that we have, or particles that we have. I is 1 to n. We're going to sum up the number of them that we have, right? But these are the names given to these entities, and also they are given different expressions. This lots of times is abbreviated as capital M, and this is called the moment of the system. Okay, these MI, XI are individual moments. Moments are the tendency to rotate, basically, the tendency to make something rotate a certain way, okay? So this is the sum of all the masses, and that has a name just called the total mass of the system, and that's given by M. Total mass of the system, the moment of the system, okay? That's what that's called, and these M1 times X1, individual moment, M2 times X2, another individual moment, tendency to make it rotate. Okay, so let's see an example. Let's go ahead and do example 1. Example 1 says this. Here is an x-axis, part of an x-axis, and what we have here are these points. There's -3, we've got +2, and we've got 8 right here. All right, and we have 3 masses in here. So at this location, at -3, we have M1. M sub 1 is 12. M sub 2 is 15. M sub 3 is 20. All right, so we got these 3 masses at these 3 different locations. So let's just say this is where 0 is. That makes me feel better to see it. Okay, so find the moment M, this guy, okay, about the origin in the center of mass x bar. So first let's calculate M. What that is, it's the sum from I is 1 to n of x sub I times M sub I times x sub I, right? Well, that is simply M1 x1 plus M2 x2 plus M3 x3, these individual moments added up. So that's simply 12 times -3 plus 15 times +2 plus 20 times 8. So that's going to be -36 plus 30 plus 160, and that's going to be a -6 plus 60, or a 154. That is what M is equal to, the moment of the system. Then they said, well, what is x bar? So to calculate x bar, we need to know the total mass of the system. And so the total mass of the system, M, is just the sum of the masses. So this is 3, 1 to n, it's just 3 in this case, right? 1 to 3. Of M sub I, so that's going to be 12 plus 15 plus 20. So that's 20, 30, 47. What is x bar? The center of mass. That is calculated to be M over little m. And so that's going to be 154 over 47. And if we divide that, that is about, what is that about? 3.28. So what this is saying is that where we could put the center of mass so that this system balanced would be at, this is 2, maybe right here, 3.28. This is where it would be balanced, okay? That is a very simple system where everything's just linear. The next thing we're going to look at is what if we have different particles in different positions, not just horizontal, but also there's some vertical movement to that. What do we do with that? So that's the next little part of this that we're going to be looking at. Okay, so now we're going to look at what if we've got different particles scattered across the xy plane and they're not just on the x-axis. So what if we had a mass here and a mass here and a mass here? Where could we put, where is the point of the center of mass where this would balance, okay? So each one of these masses has an x and a y position, right? And so this is how we can calculate, and this is just expanding on the same idea, is that the m sub y is equal to, there's a little equal sign, the sum of each of the individual masses times their x position. And so what does that mean? M sub y is the tendency of the system to rotate about the y-axis. And so if you look, that's what we just calculated. A minute ago we had this, looked at the x-axis. We were like how we were adding up the x's. See how we're adding up the x distances? That was the tendency to make this guy tilt or rotate about the y. That's what that is. So that's why it's with that little y, the tendency to rotate about the y, or the moment about y. This is the moment about the x-axis. And so if we add up all the y's, if you look at this, look at this, this is the tendency to make, oh, I can't make my arm be straight. This is the tendency to make something vertical, oh, that you can't even see that, that's clear. Something vertical rotate this way or that way, okay? That's why we're adding up the y's right there, and it's telling us how it's going to rotate about the x. So, to the left or to the right is what it's saying. So the x bar, y bar is the center of mass. We have a 2-point We need 2 points to calculate the center of mass when we have a two-dimensional system going on. So x bar will be m sub y over m, and y bar is m sub x over m. So, let's see here. And so in words, if you want to write this down, m sub y, right here, is the moment of the system about the y-axis. M sub x is the moment of the system about the x-axis, or the tendency of the system to rotate about the x-axis. All right, so let's calculate this for a system. In the next example, they say, example 2, there's some masses located at these places. So we got M1 is 5, M2 is 4, M3 is 3, and M4 is 6. And they're located at these different positions. P1 is -4, 2. And so I'm just going to ballpark this. -4, 2. This is P1. And so position 1 of mass 1 is -4, 2. Okay. And then P2 is 0, 5. P3 is 3, 2. P4 is 1, -2. And so we're, let's put, so over here at P1, this has got a mass of 5, basically. And then at 0, 5, which is about right here, this has got a mass of 4. And then at 3, 2, 3, 2, oh, maybe this should be higher. I'll put this 4 up higher. At 3, 2, this has got a mass of 3, which is 3. And then at 1, -2, down here, we've got this mass of 6. Okay, so we have this system with all these different weights in these different positions. Where is the center of mass? That's the question. So we can calculate it using these. So basically, m sub y, let's figure out what that is. That is the sum from I is 1 to 4 of m I x I. So that's going to be m1, which is 5, times the x coordinate, -4, plus m2, which is 4, times the x coordinate, which is 0, plus m3, which is 3, times 3, plus 6 times 1. And so this is -20 plus 0 plus 9 plus 6, which is -20 plus 15, or -5. That's what m sub y is equal to. We use m sub y to calculate x bar. We have to know the sum of the masses. So if we add up the masses, 5 plus 4 plus 3 plus 6, let's see, that's 10, 15, 16, 17, 18. Little m is 18. So we find that x bar is going to be -5 divided by 18. That's what we get. Now let's calculate y bar. Y bar, we have to figure out what m sub x is. And so that's the sum from I is 1 to 3 of 4. There's 4 of these guys. M sub I, y sub I. All right, so this is going to be same thing. It's going to be m1, 5, times the y coordinate, 2, plus m2, 4, times the y coordinate, 5, plus m3, 3, times the y coordinate, 2, plus m4, 6, times the y coordinate, -2. We get 10 plus 20 plus 6 minus 12. That's 36 minus 12 is 24. So we find that y bar is equal to m sub x, 24, divided by 18. I can simplify this fraction. 6 goes into both of those. That's going to be a 4/3. So at the point -5, 18, 4, 3, this is the center of mass. And so, did I do those backwards? Did I write that backwards? Let me just see if I wrote that backwards. I said m sub x. This is m sub x. No, that's right. Y is that, X is that. Okay, so I calculated that X is negative 15, 18, and Y is 4/3. That means the center of mass would be about to the left here, about right there. This is where its center of mass is. Okay, two quick examples. Now we've looked at, okay, how to find the center of mass just for something on an axis. How to find the center of mass for something for a 2D plane. Now we want to say, how can you find the center of mass for a region, okay, or a plate? So the first example here is find the centroid, which means the place where it's the center of mass, for the region bounded by the given curves. And so on your worksheet, I've written these formulas down. This is what you use. And for the development of these, they're developed in your textbook if you want to watch how they derive these and come up with these. It's an extension of the same ideas that we've been using for the first few examples. So find the centroid of this region. So we can find x bar, y bar, which is where the centroid is going to be located, by using these formulas. So 1 over the area of the integral from a to b of x, f of x dx will give us x bar. 1 over the area of a to b of 1/2 f of x squared dx will give us y bar. So we'll use that for this region right here that's bounded. So I went ahead and drew it, but if we need to know the area of this region, that's just an integral that we learned how to do a while ago. How do you find the area under a curve? Well, that's how you integrate. So A is going to be the integration of this area from x is 0 to x is 1 of the curve, square root of x dx. So let us integrate him. This is going to be, this is x to the 1/2 if I want to write it like that, which I do. So that's become x to the 3/2 divided by 3/2, which is multiplied by 2/3, and we evaluate it from 0 to 1. Okay. So this is going to become 2/3 times 1 to the 3/2, which is 1, minus 0 to the 3/2, which is 0, or 2/3 times 1, or 2/3. That is what the area is, this area A is equal to. So for x bar, to calculate the centroid, it's 1 over the area, 1 over 2/3 times the integral from 0 to 1 of x times f of x, square root of x dx. This is how we set up finding x bar. This is a very easy integral. X times x, square root of x, is going to be x to the 3/2, and you're going to integrate that. X bar ends up being 3/5. So we're going to check your work, do that. This ends up being 3/5. Let's set up how do we find y bar? Okay, y bar is equal to 1 over a, 1 over 2/3, which is 3/2, right? Let's go ahead and write it like that. The integral from 0 to 1 of 1/2 times the function squared. Okay, well, the function's the square root of x. So if we square both sides, y squared is going to be x. So this function squared is just x dx. So we integrate this. You can move the 1/2 outside. This becomes 3/4. We're going to integrate 0 to 1 x dx. This is a very simple integral. This will become x squared over 2. Evaluate it from 0 to 1 times 3/4. And for x bar, for y bar, you get 3/8. Y bar is 3 over 8. So what did this tell us? This tells us at the point x bar, y bar are 3/5, 3/8, we find the centroid where you could put a point and it would balance. So 3/5 is about like right here, 3/8 is about halfway up. This is the center of mass right there for this guy. Okay, last example is this. What do you do when you're trying to find the center of mass between two curves? This one was against an axis, was just this region right here. But this is between the curve. Example 4, it's this region bounded by two curves. This is 2. This is 2 minus x squared. That's what this parabola is up here. And this is the line y equals to x. Between these two curves, where is the center of mass? So we would use a different set of formulas, and you can see this should, hopefully this makes some good sense. Like basically these are the same, except for in this example, g of x is the x-axis, which is the curve y equals 0. So f of x minus 0 just gives you f of x. And f of x squared minus 0 squared just gives you f of x. So when you're not against the x-axis, you have to subtract it from the bottom curve. So if we have something like this, the upper curve is 2 minus x squared, the lower curve is x. We're going to set up our integrals here. So for x bar, in this case, it's going to be 1 over a. So let's first calculate the area real quick. Let's figure out what the area is going to be. The area of this is the integral from the upper curve minus the lower curve of 2 minus x squared, the upper curve minus the lower curve minus x dx from the points of intersection. So where do these guys intersect? This intersects down here at -2, -2. This is x from -2, and this is 1, 1. I believe. Yep, that's right. So we're going to go from -2 to 1 and integrate this guy. So this becomes 2 minus x squared minus x dx. I just copied that over. This is 2x minus x cubed over 3 minus x squared over 2 from -2 to 1. And when you evaluate that guy, you find out that the area is 9 halves. That's what the area is equal to. So now let's set up these integrals. X bar will be equal to 1 over a, or 1 over 9 over 2, or 2 over 9. So we start here. X bar is going to be 1 over 9 over 2 times the integral from -2 to 1 of x times f of x minus g of x. F of x is 2 minus x squared minus x dx. This is the integral we set up. 1 over 9 over 2 can be thought of as 2 over 9. And then we have y bar is equal to 1 over a, again, which is 2 over 9. We're going to integrate from -2 to 1 and times a 1/2, right? And then this is going to become f of x squared, which will be, f of x is 2 minus x squared. So this will be 2 minus x squared minus g of x squared minus x squared dx. Okay, let's integrate this one. I'm going to push the 1/2 out over here. So 2 over 9 times 1 over 2, the 2's will cancel, and I have 1 over 9 out here. -2 to 1. If I square this, this ends up being a 4 minus 4x squared plus x to the 4th minus x squared dx. And so 1 over 9, -2 to 1, 4 minus 5x squared plus x to the 4th dx. These are all very simple integrals. 4x minus 5/3 x cubed plus 1/5 x to the 5th, evaluated from -2 to 1, will give us this answer right here. What do I get for that one? Y bar gave me 2/5 after all of that. Okay. X bar, when I did that, what did I get for x bar? I got -1/2. All right, so what this tells me is that the centroid, or the center of mass for this system, is located at x bar, -1/2, y bar, 2/5. Or -1/2, 2/5, about right here. That's the center of mass for that system. All right, center of mass.